to do question 1. Now in this little equation, the 1 is a 1, s is d by dt, the Laplace variable, and then k, where should you put it, k is called the steady state gain, and t is called the time constant. So with this block diagram now, k is called the steady state gain, t is called the time constant. And we can also have an equation now. If we put a step in here, we'll get an output here, which is a graph that looks a bit like that. This is output against time. And we can have a little equation for this, which I'm going to put up here. And the equation is that y of t, this is the step response, y of t is given by k into 1 minus e to the minus t over t. Now in this equation, little t is time and big T is the time constant. So this is called the step response. So for first order systems, question 1, that's what you need to know. That's all you need to know. And knowing that just that bit of information there, you can pick up 10 marks. Okay, so let's look at some examples now of how we could use this bit of information to pick up our 10 marks. And we could do that by looking at the exam paper from 2020, shall we? Okay, so got that. This is I'm just going to move this back a bit because it gives me a bit of space here. I've just got about, it's quite good. This is about a meter from here to here. So if you go use a meter, I'm not in the picture like this, and you can see it quite well. If I back off to about here, the light gets good. Right, so I'm just going to do, so this is just to recap them. This is the structure of a first order system, K1 plus ST. Got half a 1 there. K is called the steady state gain, T is called time constant, and if you put a step into this system, you get a response shape that looks a bit like that. And the equation that describes it is y of t is k into open brackets 1 minus e to the minus 1 minus e to the minus little t over t, where little t is time. And that's what we've got to remember. Somebody's phoning me up now, but my assistant will answer the phone hopefully. My landline hasn't been working today. It's been broken. It's got mixed up with somebody else's line. So when you phone, it phones 2 numbers at the same time. Right, nuisance. It's because they messed about with the cables over the weekend. Right, here, so this is now exam question paper from 2020. So that's last year. 2020. And this is, they all start off with a little block diagram. They all start off in roughly the same way, which I'll go and explain as we go along. So you're given a block diagram now, and this is given by K1. This is given by K2 regress. This is K3. Another box with a K4 in it. So you're given some sort of block diagram as the first part of question 1 always. You're given a bit of a block diagram, and it's usually of this structure. It's got like about 3 or 4 feedback loops, and otherwise it's too simple, isn't it? If it's just a, and you're asked now to simplify this down to the form K over 1 plus ST, and you've got to work out what K and T are, the steady state gain and the time constant for this system. Okay, so this is the type of thing you get. It's not worth many marks, this, but anyway, nothing is it? Anyway, that's the first part of the question now. This is question 1, part A, and I was quite kind to you last year, or not to you, but to the students. I actually gave them the answers. It did a show question. You can't quite see this, but if you look at the paper, it gave the answer in there and said, show that this could be simplified to a certain thing. So at least I've got the answer to check I've done it correctly. So I'm going to do this now. Well, so it involves now a bit of block diagram simplification. I'm going to put that in my pocket rather than have it over here. So the first thing to do is to call that, say, V, and call that Y. Okay, that's V and Y, and then follow all the signals round. So that signal there will be this times that, so it'll be K4Y. That signal there will be V plus V minus K4Y. And that signal there will be that times that. So it'll be K1 into V minus K4 times Y. This signal here, the one going down there, will be K3 times Y. That signal there, I should do that actually, that'll be K3 times Y, and then we can work out what that one is. So this will be this one minus that one, because it's a plus and a minus. It's this minus this times this, so that signal there times that is equal to that. So we can get a little equation now, which I'm going to write down here, but I'm going to move it up here in a minute. So the equation will be Y equals, that's this signal here, is this thing here, which is K2 over S, multiplied by this signal here. Now this signal is this one minus that one. So it's going to be multiplied by K1 V minus K4Y minus K3Y. So there's our little equation now, describing what's going on in the system. That signal there, that's the Y, equals this one times that, and that signal there is this one plus this one minus that one. So there's our little equation. Now we've got to rearrange this now, rearrange this in the form of K over 1 plus ST, because we need it in first order time constant form. So you rearrange this equation now into this format. Okay, so the first thing I do with these is move whatever you got down here up here. So I could delete that and put an S in there, couldn't we? Okay, so then we could also have a go now at expanding some of this out. So I get SY is equal to, then I'll get K2 times K1 times V. That's K1 or K2 times K1 times V. And I'll get a minus K2 times K4, K2, K4 times Y. So I've got that, it's actually times K4 times K1 times K4, so I missed a K1 out there. So that'd be better as K2, that's that one, times K1 times K4 times Y, minus K2 times K3 times Y. So just make sure I've done that right. So I've got that times that goes in there, then I've got that times that goes in there, and then that times that goes in there. And then I've got some Y terms here, some V terms, and those Y terms. So these Y terms can join in with these. and I'll get the S. I've probably got just about enough room for this, haven't I? S plus, because when these move over now, they change sign. So it'll be S plus K1, K2, K4 plus K2, K3 times Y equals K1, K2 times V. Now what I've got to do now is move this term here now underneath there. So I could move the board down a bit more, but I'm running out of board here. So I'm just going to rewrite this equation here up here somewhere. Okay, so it's going to be K1, K2 over S plus so we get now this here. So get the K1, K2 and the S plus K1, K2, K4 plus K2, K3. So this becomes the, and this is what I asked for in the answer. That was what you had to show it was equal to. You probably can't see this, but you might, no you can't because I've switched the autofocus off. Anyway, that was the answer and you got a few marks for that. It was a show question. The second part now is to convert this now into the form K over 1 plus ST. So the problem with this now is this term here now should be 1, shouldn't it here? So we have to divide everything through by this. So you're going to rewrite this now as Y equals K1, K2 divided by K1, K2, K4 plus K2, K3 divided by 1 plus S divided by K1, K2, K4 plus K2, K3. So I've done to take this expression here now and divided everything through by that term. So that, when you divide this by itself, it becomes a 1. This one becomes that divided by that, and then this is S there, and this term here is 1 over T, isn't it? Sorry, you can't see that because there we go. So that. So here is that the answer now. And then you could say that this term here is K, and 1 over this term is T. Okay, because that's like 1 plus ST, so T is 1 over this. So it's like 1 over that. I could move the S over there somewhere. That term there is T, so T is 1 over this, and K is that term there. And that was quite a big chunk of that question. Then there's a simpler part to it then, which I'll go to next. So I'll just go back to here. So what I did then was I gave you some numbers. I gave you some numbers for K1, K2, K3 and K4. So it said that K1 was 1, K2 was 2, that's quite easy, isn't it? K3 was 3, and K4 was, I've chosen some stupid number here. I chose 2 rather than 4. But anyway, they're the numbers now. So you're given K1, K2, K3 and K4, and you're asked now to work out what the time constant on the K is. So this is quite easy. All we've got to do is go back now to this equation here. I'll just try and get in. Go back to this equation here now and just put the numbers for K1, K2, K3 and K4 into this expression. That'll give you the K, and that'll give you the 1 over that will give you the T. So you just stick the numbers into those expressions. Just to show you what I mean, in case you're confused, but it shouldn't be. I'll have to rub this out now because I haven't got much. I'm running out of space on my board. you can see now, this is quite straightforward. It's straightforward for me, because I've been doing it for donkey's years. It's a bit sad that Prince Philip died this week. I didn't have any real association with Prince Philip, but he was the Vice Chancellor of Salford University for 26 years, and in one of those years he actually awarded me my PhD. So I went up and shook hands with Prince Philip in Maxwell Hall and got my PhD. So that's my only association with Prince Philip, but at least it was an association. So we got now the K was given by K1, K2 over K1, K2, K4 plus K2, K3. So what we do is we just stick the numbers K1 is 1, K2 is 2, K3 is 3, K4 is 2 into that expression and get K. And then T was given by 1. Well, we'd worked out that number, wouldn't we? So 1, T is just one number. K1, K2, K4 plus K2, K3. So again, we just put the values for K into that expression, get T, put the numbers of K's into this expression, get K. That was dead easy, wasn't it? And the last part now, so when we did that, I've got the answers here somewhere. I cheated. I'll just put the answers in. So K came out as 0.2. So K, how should you do it? This is equal to, K came out as 0.2, sort of back to front, and tau came out as 0.1. So what we've got now is tau is 0.1 and K is 0.2. So that was the answer for this bit here. So we got those in the bag. So I'm just going to rub these out. And maybe just rearrange these. So K came out as 0.2, T came out as 0.1. So we'd work those out now, just by putting the numbers in. And the last part now was to do, well, the last part is always to do this equation, you know, the equation y of t is k 1 minus e minus t over t. It uses that, uses this step response equation. I've got to check you out on this equation here somewhere. So what I did was, it asked to find the time t at which was equal to 80% of the total value. So we know now that the total in the step response, the final value is k. So 80% of the final value will be 0.8k, won't it? So imagine drawing a line now along there. So that is 0.8k. And we're finding out the value of time at which that occurs. So what we do is now we just put the numbers into this equation. So y of t is 0.8k. So we get 0.8k is equal to k into 1 minus e to the minus t, and then little t was 0.1, wasn't it? So 1 over 0.1 will be 10. So here's the expression now that we've got to solve. So we've got 0.8k, that's 80% of the total, is equal to k into 1 minus e to the minus, and this is t over t. Now what's nice about this is the k's cancel, so we don't need to know k anyway. That cancels out, and then we can solve this then for little t, which is time. So if we take, say, this onto this side, so we get that 0.2 is equal to e to the minus 10t. And then we can solve this by taking natural logs. So we'll get natural log ln of 0.2 is equal to minus 10t, and then t will be natural log of 0.2 over minus 10. Okay. So you can, I don't know what the natural log of 0.2 is, but there's a thing on your calculator that'll work it out. And that now is a typical first order system question, question 1. And that was worth, the whole thing was worth 10 marks. But the exam now is marked out of 160, isn't it? So it's not a lot of marks really. But it's 10 out of 160. It's better than 0 out of 160, isn't it? Okay, does that, any questions on that? If you got any questions, just pop them up in the, and I'll try and get these solutions, these questions and the solutions are in Blackboard as well, if you have another look at. So let's just do one more, shall we? Should we do 2019? They're all quite similar, these questions. So I've got my Timberland boots on today and I'm a bit clumpy in them. End up kicking the tripod. I'll get told off anyway, somebody will go mad. Kicking the tripod. Yeah, somebody's going mad about kicking the tripod. Let's simplify the block diagram, do it more slowly, okay. I shall slow down. Right, so this is 2019 now. This is well before COVID, isn't it? This is before we'd ever heard of COVID. And it's a similar sort of thing really. They're all quite similar, these. I try to make them similar but different as well, so you've got an idea of how to do them. I think since we last spoke, Man United have done quite well and Everton have done really badly, so we've not had any luck, Everton. But Man United have done quite well. City did okay till they lost to Leeds, but still City's still going to win the league, aren't they? So you can see this is not that dissimilar to the one we did before, but I've got a bit of leeway. I can label the K's different things. I can put a different thing in there. Got a bit of leeway to do this. And so what I ask you to do is simplify this down to a single block. That's the first thing to do. And I, again, quite generous here. I actually give you the answer there. You can't see it, or you can probably the autofocus, it doesn't work. Anyway, it's the trouble with this. The webcam was only about £100. If I'd spent £1,000 and it would have been good, but I couldn't get one. So let's have a go at doing this one. So I'll go a bit slower this time. So what you do is you start off over here and you follow all the signals round until you get that signal there. And then you say this times this equals this to get your equation. It's always the same. So this signal here is going to be this times this. So it's going to be K1 times Y. And that signal there will be this one plus this one minus this one. So it's going to be V minus K1Y. And that signal there, this will be this times this. So it'll be Kp into V minus K1Y. So that's that signal there. Then this one here will be K2Y. So that signal there is K2 times Y. So this signal here now, which is the one we want, is going to be this one minus this one, because it's a plus and minus here. So I've got a bit of space to do it, haven't I? So it's going to be K. So that signal there now, or I can say Y, if you like Y, that's this one here, is this times that signal. So it's going to be y equals 1 over s plus 2. So that's this times that. But that signal there is this one minus that one. So it's going to be open square bracket, say kp v minus k1y minus k2y. So this now is the equation which describes what's going on here. So just go through it again. Start off here, label that y. So this one, this signal is this times this is that. And with a block diagram, it's like this. If you've got a block diagram, then C is AB. This is that times that. That's how it works. This one, the output, is what's in the box times the input. It's not. It's how it works in feedback control. So we get, looking at this, this is K1Y. This is a plus and minus, this is plus V minus this. It's going to be V minus K1Y. Then this one here, this is going to be this times this. So it's going to be KPV minus K1Y. Then this signal here will be K2Y. And then you got plus this minus this. So that's what that is. So that's that signal. So it's that signal times that box is equal to that. Which is that equation there. And then we have to rearrange this then in the form of y equals something times v. So the first thing to do is take the s plus 2 and move it up here, because that's easy to do. So all that disappears, and we can have this as s plus 2. Then what we can do is we can expand this out now into the v's and the y's and bring the y's over onto this side to join in with this one here. So then we'll get s plus 2. That's that bit there. Then I've got a kp k1 times y, but it's a minus. But remember, it jumps over this sign, changes sign. So the minus becomes a plus. So it becomes plus kp k1. That's the kp k1. And a minus, again, becomes a plus on this side, plus k2. Then that's multiplied by y, because it's kp k1y and k2y. And that's equal to kpv. Then last thing is to move this term here underneath there. So then get that y equals kpv of s plus 2 plus kk1 plus k2. So I just move this term here goes underneath there to give me this thing here. So it's kpv of s plus all that stuff there. So that's the answer then. So you can see they're not that dissimilar to every year, but they are different, but they're not that dissimilar. Then your next trick is to convert this now into the form of k over 1 plus st. So this is quite similar to what we did last time. So we've got this expression here now, and we need to convert this into the steady state gain and time constant form. So I'm just going to have to use the board clean and brush every time. This question isn't so, you can't use MATLAB to do this one. There's only some of the questions you can do with MATLAB. This one you can't. Right, so I'm just going to move this a bit closer to here. There we go. So this is our little thing we've got so far. And we've got to write this now in the standard form of k of 1 plus st. So we've got to make this term here, the 2 plus kp k1 plus k2 into 1. So to do that, take this term and divide it by itself. Because if you've got, like, say, a, b, c, d over a, b, c, d, then it's equal to 1. So no matter what you've got, as long as you put the same thing underneath, it'll always be equal to 1, won't it? So we can rewrite this now as kp over 2 plus kp k1 plus k2 divided by 1 plus s, and then 1 over 2 plus kp k1 k2. So we can write it in that format, and then this term here then is the k, and this term here is the t. So t is 1 over that term, and k is that term. So that was the next part of the question, to work out expressions for k and t. Yeah, I'll explain that again. So what you're trying to do now is, imagine you've got some expression, say 20 over s plus 40. Okay, and you've got to make this into a 1 here. So to make the 40 into a 1, you divide it by 40, don't you? So you could rewrite this by dividing everything through by 40. So we get 20 over 40 over s over 40 plus 1. Because 40 over 40 is 1. That's 1 over 40. That's 20 over 40. So whatever that term is there, if I divide everything through by that, I'll get a 1 there. And then this is in the standard form then of the k and the t. So what I'm doing is I'm taking, this is the s here, this is the rest of the rubbish here. This is all that I'm left with. So if I divide this expression by that term, then I'm going to get, like, this sounds like it's going to be kp v over 2 plus kp k1 plus k2. That's that term there, divided by, and then again s over 2 plus kp k1 k2 plus 2 plus kp k1 k2 divided by 2 plus kp k1 k2. So I've taken this expression here, divided everything through by that. So it's, this goes underneath there, this goes there, and then this goes there. But now that over that, they cancel perfectly. So it's equal to 1. So this bit disappears and becomes a 1. And now it's in the time constant form, because it's a 1 there. Then this term is the DC gain, and this term here is the time constant. This is like k over 1 plus st. So that's the k, there's the 1, there's the s. So this term here, like that term there, 1 over 2 plus kp k1 is equal to t. It's quite straightforward. Well, if you've not done it before, it's not straightforward, but this is how you do it anyway. So, good question now. I'm just going to move this back to give me a bit of space to get it on my board. Right, so look what the next part of the question was. I've rubbed it all out now. What a twit. It then says, it gives you values for kp. It says kp is 30. It gives you k1 as 0.1, and it gives you k2 as 7. So it gives you some numbers now. So just going back to where we were with this. I shouldn't have rubbed everything out. I was too quick. No, it doesn't matter too much. So we've got expressions now for k, haven't we? K is equal to kp over 2 plus k1 kp plus k2. That was the expression I had for k. So I can do is put these numbers now. So you've got that expression in the first part. You've just been given these numbers now. So you put these numbers into here. Okay, so this becomes 30, because kp is 30, over 2 plus k1 times kp. So that'll be 0.1 times 30 is 3, plus k2, which is 7. So that's 30 over 12, isn't it? So k is 30 over 12. And the time constant t is just given by, t was given by that. So that term there is 12. So t equals 1 over 12. So we could work out k and t now, given these numbers. And then the very last bit then is to find the time it takes, and this I can just give you different numbers. So this time it says 50% of the final value. So it's to find the time to make 50% of the final value. So that's using now the standard equation, isn't it? The equation y of t equals k into 1 minus e to minus t over t, that equation. And what we're after this time is 0.5k, because it says 50%. So 50% is half of k, isn't it? K is the steady state value. 50% of it will be 0.5k. So get that 0.5k into 1 minus e to minus t, and then the time 1 over t. 1 over t is 12. So, or t is a 12th, so 1 over t will be 12, won't it? So this will be 12t here. 12t. Then the k's cancel, and then you can solve that equation for t, just like we did last time. So this time it will become 0.5 is e to the minus 12t, and so natural log of 0.5 over 12 is t. Again, you'd have to use natural logs in your calculator to do that. So there's two, not too bad, 4 o'clock. There's 2 questions there. That was the first order systems part and 2 past paper questions for you. That's 2019 pre-COVID and 2020 COVID. So they're quite similar, independent of COVID, the questions. And both those 2 things were both worth 10 marks. And that's my revision for you on first order systems. If you watch the videos, do have a go through these. There's another exam paper to have a go at as well. Have a go at doing them. And the questions are likely to be very not the same, but similar type questions, different numbers, but the same sort of concepts. So that's our first order systems done. So we can now move on to second order systems. So second order systems there's a special format to second order systems, and that's k omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is our format now for a second order system, and k again is the steady state gain, but this time omega n is called the natural frequency, and zeta is called the damping ratio. Okay, and what we typically have to do in these sort of problems is to have a closed loop control system, simplify it down to this structure here, simplify it to this, and then pattern match to work out what the natural frequency and damping ratio is. So that's how these questions tend to work. So if we go back now, I've got 2018 here, but we're doing 20. We'll go back to 2020, shall we? Just going to find my 2020 question. Okay, so the thinking behind this then, it's quite straightforward. There's two parts usually to the second order systems one. There's two little sub questions, they're usually the same sort of sub questions you get. So the first one is where I give you some block diagram. You've got to simplify it to this form here and then work out what your natural frequency and damping ratio is. So we'll try and do that over here somewhere. So in this particular instance, we were given a little block diagram. Look like this. So we're given now these block diagrams can't be that complicated, otherwise they won't be second order systems. So we've got a little block diagram like this now. It's got a little second order system in there, a bit of proportional control here, say, and a block diagram. Got to simplify this block diagram to a single block and then pattern match it against this here and work out what omega and zeta are. That's usually always the first part of the second order system question. So if we call that V and Y, that signal there is V minus Y, and that signal there is 4 V minus Y. And so we can say that this is this times this to give us that Y. Now 4 fours, it's a bit tricky. Use your calculator if you can't do it, but I think 4 fours is 12. No, it's probably not 4 fours. Let me think. Count my fingers up. 4 fours, 16. So it's going to be 16 V minus Y over S plus 1. So that's this is this times this. So it's 4 fours is 16 V minus Y over S plus 1. And rearrange this now in the form of Y equals. So move this term up here. So I'll get S squared plus S times Y is 16V minus 16Y. Then make the Y's go over onto this side. So I get S squared plus S plus 16 times Y equals 16V. And then I can move this term underneath, then it looks like one of these. So I'm going to write that over here. So that's equal to, it's going to come out as 16 over S squared plus S plus 16. So I've got this term here now, and that's the same as this. So we could look at this now, and we could do a bit of pattern matching. So we could say that this term here, because we've got a 1 there, that's the same as that one. And therefore this now has to be the same as that. So omega n squared has to equal to 16. So omega n, if omega n, where did the V go? Well, it is V, isn't it? So this is, put a V in there if you like. No, this is a block diagram, isn't it? This is a block diagram with V in and Y out. So it's saying that Y equals that times V. This hasn't got a V in either. It's just a transfer function. It doesn't matter about the V anyway, to be honest. That's a sort of, you're not looking for that. You're just looking to match that number there against that number there. So I've made the question quite nice. 4 fours are 16. Square root of 16 is 4. So omega n is 4. We then know that 2 zeta omega n is 1, because that's got to be the same as that. That's got to be the same as this. So we know now that 2 zeta omega n is equal to, that's that term there, it's got the same as this number, and that's a 1 in there. You can't see it, but it's a 1 because it's s on its own means 1 times s is equal to 1. But we know now that omega n is 4. So 2 times 4 is 8. So zeta is 1 over 8. So the answer was, you have to put 8 units on these. This is sort of in radians per second. So omega n is 4 radians per second, and damping ratio is 1 over 8. So that's the sort of typical little first part of second order systems. It's always going to be like that. You're going to get a block diagram like this, simplify it down into standard form, and then do a bit of pattern matching to get omega n and damping ratio. So I'm trying to check out you can do that type of skill. Okay, that was the first part. Now, with second order systems, there's a few like extra equations that you've got to know. So I'm just going to go through the equations now, because some of these equations could come up in the exam. Or come up in the exam. Now, with second order systems, you can get different types of response depending on the damping ratio. And if the damping ratio is less than 1, it's called lightly damped, and you get some interesting behaviors. If the damping ratio is equal to 1 or bigger than 1, it's not so interesting, and there's no real good equations for it either. So in the exam, it's always fiddled, so the damping ratio is less than 1. Because if the damping ratio is less than 1, there's extra equations we can use. And let's explain what the equations are. So this is a typical second order system response now. Here's a second order system response for a lightly damped. This is damping ratio less than 1. Looks like this. So it comes up, this is called an overshoot here, an undershoot and an overshoot. And this is called the peak overshoot here. And if we draw a line down there at the peak overshoot, the first thing we can do is, this has got a frequency associated with it, and it's called omega d. And the omega d is omega n into the square root of 1 minus zeta squared. So omega n is natural frequency, n for natural. Omega d is for damped. This is a damped frequency, and it's given by omega n into the square root of 1 minus zeta squared. So you've got to know that one. This time here, which I tend to call t star, that is given by pi over omega d. So once you've worked out omega d, you could work out the time for the peak overshoot using this little formula here. And then the final formula is the logarithmic decrement equation. And that gives you the ratio of, say, x1. So it gives you the ratio of that distance to that distance. It gives you how big the peak overshoot is. And that's given by x2, could fit in here, x2 is equal to e to minus zeta pi divided by the square root of 1 minus zeta squared multiplied by x1. So in addition now to knowing this equation here, you also need to know all these equations as well. But they're all on the board there for you to see. So this is for damping ratio zeta less than 1. Damping less than 1, we've got an equation for the frequency here, omega d, got an equation for the peak overshoot time, and we've got an equation for the it's all in the power. That's all. That's just one term. That's one term. So it's e to the minus zeta, that power, that term. So it's zeta pi divided by the square root of 1 minus zeta squared. That's just one number, and it goes in e to that number. Okay. And so when you've got now values, for omega n and zeta, I could ask you to work out any one of those numbers. So once you've got these two numbers here, you could plough omega n as 4 and zeta as 1/8 into either that expression, or that expression. So you could work out now what omega d is, what T star is, or what x2 is, the overshoot. And I can ask you any one of those. But it's quite easy, isn't it? Once you've got these numbers, you just plug them into here. In this particular case, in this exam, I asked you what the peak overshoot was. So you have to put a damping of 1/8, which is 0.125, into there and work that out. I don't know if I worked that myself or not. No, I didn't work it out. But you can do that. You can compute that, can't you? It's quite easy. Now, so in this first part of the question, you're given a KP and you have to work out these numbers, the omega n and the damping ratio. For the second half, it's backwards. I give you, say, a damping ratio, and you've got to work out the KP. So it's with the same problem, but you're using the equations backwards. It's a bit sneaky. So the first part is always very straightforward like this. Get a nice little block diagram, simplify it to a single block, like that one there, the 16 over s squared plus 16. Do pattern matching to get omega n, stick the numbers into these formula. That's the first half of your second order system question done. For the second half, I've got to rub all this out and go back to my original block diagram. So I'll just do that. The only sort of advantage I can see of all this COVID stuff is I've made really good notes for next year, and good revision material for your final year, and good videos of how to do the assignments and everything. So I'll release those on YouTube next year when you're doing the course, so you'll have extra learning materials to use. That'll be handy. So in this last part now, it's the same block diagram, but this time there's a KP in there. In the previous example, it was a 4 in there, wasn't it? So I've said now, okay, what value of KP do you need to make the closed loop system critically damped? This is a different type of solution now, where you've got to know critically damped means damping ratio was 1, but it could be anything, and I can make it damping ratio 0.7 or something to give you that. So in this particular case, it's damping ratio 5.1. So find now the value KP that makes this system critically damped, and that's the last part of the question. So it's always the same in these questions. The second half now, I put a KP in there, and I give you some omega n or damping ratio or something, and ask you to find the gain KP. So it's similar style to what we did before, but not obviously quite the same. So I should have drawn that a bit higher up really, but up here somewhere, then I'd have had more space down here. The camera hasn't got a very good, it has got something that allows it to stay like a stick. It's fairly sticky, isn't it? Not too bad. I've got a bit more board down here now. So rub this out and put some labels on, V and Y. So that's going to be V minus Y, and that's going to be KP V minus Y. So it's not quite high enough, is it? So this signal here will be V minus Y, and this one here will be this times this will be KP V minus Y. And then we said that Y is this times this to get our little equation. So Y will be given by 4 KP V minus Y over S squared plus S. I can move this term up here, so I get s squared plus s is equal to that, and then I can move the y over as well, so I get s squared plus s plus 4kp times y equals 4kpv, and I can write this as y is 4kpv over s squared plus s plus 4kp. Now, what I want is, I want the system to be critically damped. So if we think of our second order system now, it's s squared plus 2 zeta omega ns, omega n s plus omega n squared. This is our classical now second order system equation. And what we want now is, that term there is not very good zeta, is it? But that is zeta. That is the damping ratio. So we want the damping ratio though to be critically damped, which means it's 1. So because it's a 1, it would disappear, wouldn't it? So that term is actually 2 omega n. So new pattern matching now, s squared is the same as s squared. So 2 omega n is equal to 1. And 4kp is equal to omega n squared. So I can use the first equation now, which says that 1 equals 2 omega n. So that's quite a nice equation, isn't it? 1 equals 2 omega n. So omega n equals 0.5. And then I know then this term here will be omega n squared. So omega n squared will be 0.5 times 0.5. So omega n squared is 0.25. So 0.25, so omega n squared is 0.25, but that's the same as 4kp, because that's the same as that, that's the same as that, that's the same as that. So that's equal to 4kp, and therefore kp is equal to 0.25 over 4, which is 1/16, isn't it? So if I set kp as 1/16 in here, then that system would be critically damped. And that was that second order system. So if you've done that whole thing right, another 5 and 5, 10 marks. Okay, that was 2020. So if we go on to just like I'll show you. If you do, I'll do part B of 2018 just for a bit of a change. So we'll do another second order system now. This is from 2018. The 2018, 19 and 20 are on Blackboard with the solutions. That's Dr. Ulan's part and my part. So not everyone puts solutions up, but I do. So we'll just do one more now, second order systems equation example, and then we'll have done question 1 quite well. You should then be able to have good got question 1 and get a load of marks. So let's see what we've got here. So let's go on this. 6 over s plus 4. So there's a little block diagram. I'm going to extend this question slightly. So this is the problem that you were given in 2018. But I'm going to add a little bit to it, not to make it any more harder, but just to make it more sort of compatible maybe with typical things you might get in this year's exam. So it could start off now saying if KP, let's say is, what should we choose a number for KP? Say KP is 2. Say KP is 2. Find out what the natural frequency damping ratio of the system is. So that could be the first part. Then the second part might be find the value of KP to give it a natural frequency of say 10 radians per second. And the third part, we change the controller slightly to make it into a proportional plus derivative controller and ask for it to be critically damped. So I put three sections in this. In the exam we'd only get 2, but it just gives us a bit more coverage, doesn't it, of this type of problem. So first part, say A, would be KP equals 2. Find omega n and damping ratio. This is very sort of typical thing that you tend to get almost every year. Should we go and do that first? So what you've got here now, you're told that is 2. So you've got to simplify this now down to a single block. Second order system block, compare coefficients, work out omega n. This one you could do in MATLAB, as a matter of fact, if you wanted to. But it's so easy, you don't need to do it in MATLAB. So call that V and call that Y. So that'll be V minus Y, and that'll be 2V minus Y. I said that's wrong, I made a mistake already. In 2 plus A. So this, you have to start off standard procedure. Start off here, follow the signal shroud. That signal there is actually 10y over s plus 10, because that signal there is this times this, and therefore this one here now is actually v minus 10y over s plus 10, and that signal there is 2 into v minus 10y over s plus 10. So just follow the signal shroud. That's going to be, this one is that times that gives you that one, is plus v minus this one, then that one is this times this, that's 2 times that, and you can say that y is last box times the last input. So we can again get our equation, which is that y equals 6 over s plus 4 times 2 times v minus 10y over s plus 10. So there's our equation now. Now, one thing to be careful with here is this term here. So it's like a term with fractions in, and it's always prone to making an error, this. So we could write v minus 10y over s plus 10. We could take that term there, and we could multiply now top and bottom of this by s plus 10. To give it a common denominator. So we could rewrite this as s plus 10 times v minus 10y over s plus 10. So what we're doing is we're just going to put this term here under a common denominator of s plus 10. So it's going to look a little bit different. It's going to look like this. So that looks like that, and the advantage of this now is we can remove these two terms now. We can move them up here to make our maths a bit simpler and a bit safer as well. So we rationalize this. It's like having, say, 2 plus a half. You could say this is the same as 2 times 2 over 2 plus a half. So 2 2s are 4, 4 on 1 is 5. This is the same as 5 over 4. Obviously 2 plus half would be 5 over 4. It's just bringing it under a common denominator. Now the advantage of that method is you can then take this term and just move them up here. They just disappear like that, and you get an s plus 4 times an s plus 10 there, and then the calculations then are much simpler. So it's going to give us s squared plus 14s plus 40. That's s squared, 4 and 10 is 14, 4 10s are 40. Now on this side we've got 6 times 2, so we could rewrite that as 12, couldn't we? 12. And then I've got 12 v to s plus 10, but I've also got 12 times minus 10y. So it's going to be 120y, isn't there? But it's minus on this side, plus on this side. So it's going to be plus 120 times y equals 12 s plus 10 times v. So 40 and 120 is, what tricky this, 1 something, 20, 30, 40, 50, 60, 70, 80. No, it's not 80. It's going to be 160, isn't it? And so we can finally rewrite this now as move this term underneath there. So I'll write it over here, okay? So it's going to be 12 s plus 10 over s squared plus 14s plus 160. So there's my simplified transfer function. I've simplified this down to this, and this is going to be the same now as my classic second order system equation, which is s squared plus 2 zeta omega n s plus omega n squared. So you've got to remember this equation now. The s squared plus 2 zeta omega n s plus omega n squared, and you can say that omega n squared is 160 and 2 zeta omega n is 14. So that gives you some equations to solve then. Omega n squared is 160, so omega n is the square root of 160. I've got no idea what that is. And then you know that 2 zeta omega n, should do it here, 2 zeta omega n is equal to 14. You know what omega n is, so you can solve that for the damping ratio. So that way you could go for some number in there. Sorry, some number in the block diagram, and you could work out what the natural frequency was and what the damping ratio was. That's a sort of typical thing you might get in the exam. The second part of the question was, if we change this now to a KP, so you can see what I've changed out. It's the second part, I've changed it from a number into a variable, and then you've got to find that KP then to give a certain natural frequency. So this time I said the natural frequency had to be 10 radians per second. So I want omega n now to be 10 radians per second. What value do I need to choose KP to get that? So it's a similar sort of problem that we just did. The difference is when we come to match it now, that omega n squared will be 100, and these equations here will have some KPs in. So let's rub some of this out, shall we? So what we want is omega n is 10, and I'm just going to get rid of my piece of paper. Right, so again, we have to do a block diagram for this. So this is going to be V minus 10y over s plus 10. And that signal then will be Kp this time into V minus 10y over s plus 10. And then that will give me, I'm just going to move, don't know where to move to really. It's not so, it's okay down here, isn't it? So we can say that this is this times this. So I'm going to get that y equals 6 over s plus 4 multiplied by Kp. And I'll do the same trick with this now. I'll make it s plus 10 times v minus 10y divided by the s plus 10. So same trick as I did before. And so there's my little system equation now. This y is this block here times this term here. So it's Kp, and that simplifies down to that. I can move these two terms now up here. So I'll then get s plus 4 times s plus 10 times y, and those two will just disappear. So this time I'm going to get s squared plus 14s plus 40. That's s squared, 14s plus 40, that's coming from that term there. And then I'm going to get a 6 times Kp times 10. So 6 times 10 is 60, so it's going to be plus 60 Kp. That's going to be equal to y. That's equal to 6 Kp s plus 10 times v. And this equation here now, this is our second order equation, isn't it? This is the same as s squared plus 2 zeta omega ns plus omega n squared. And what I want now is I wanted omega n to be 10. So omega n squared, I've chosen nice numbers for me, 10 times 10 is 100. That term there's got to be 100. But that term there is equal to 40 plus 60 Kp. So 40 plus 60 Kp has got to equal to 100. So it's quite a complicated equation, this one now. 40 plus 60 Kp equals 100. And I got that by saying this term here, I wanted an omega n of 10. 10 times 10, can add 10 times up 10, but I think 10 times 100. And then that's going to equal to the term here, which is given by 40 plus 60 Kp. So there's my equation now to solve. And you can see from this that Kp is 2. Oh no, it's not, it's 1. Kp is 1. Because Kp is 1. So if we put Kp as 1 in there, then that system would have a natural frequency of 10 radians per second. Okay, so that's 2 past paper questions now that I've gone over on first order systems and second order systems. And if you watch these again and watch the videos, then you should be able to do question 1 very straightforwardly. So that's our first bit of revision done now. So thanks for listening to that bit of revision. And next week we'll move on to question 2, which is Hurwitz stability test. So there's 2 topics to cover this week, so it took a bit longer than normal, but still a bit, it's past 5, isn't it? So that's a bit of revision for you there on first and second order systems. So next week now we shall move away from this to the next question, which is question 2. So question 2 is Hurwitz stability. So remember, it's called Adolf Hurwitz. Adolf Hurwitz invented this. It's nothing to do with Adolf Hitler, but anyway, it was called Adolf Hurwitz, and he invented this in about 1892, which is quite a long time away ago, isn't it? 1892. And we look at the Hurwitz stability test next week. Okay, so happy with that. I felt we got quite a bit covered there. You should have a good go now, shouldn't you? You can watch the videos, watch these videos again. They're all stored on Blackboard, remember these. They're recorded so you can watch them. And have a go at some of the examples. And they're all going to be like of this type. No catches, no nasty questions, no things you haven't seen before. And so next week now, we'll start off at 4 o'clock and we'll do Hurwitz stability. I'll go over the Hurwitz stability concept and then we'll do some past paper questions. Okay, so I'll do 2 or 3 past paper questions. And on that note, I'm going into Salford tomorrow to do a lab. So I'll be there all day doing labs for the final year. And I hope that to see you next year in Salford, in Newton or something. Oh yeah, it'll be in Newton still, won't it? And hopefully you'll have had a COVID jab by then, or maybe you won't. Maybe it's not safe for you to have one. Who knows? Anyway, I can have my COVID jab. I've had one. I'll have another one soon, and hopefully survive it. And found that useful. Don't know about you. Was it okay? Up or down? What do you think? No, not many people saying anything. Yeah, you okay on that? It should be fine. We've got another 3 weeks for revision, haven't we? Just keep on going with this. You can't. The problem with the exam is that only half the questions are mine. The other half from Dr. Ulan, who are really dodgy, aren't they? So that's the problem. It's not that what I'm doing is hard, but it's the Dr. Ulan stuff is a bit more tricky, isn't it? More tricky stuff. But anyway, that's how life goes. So thank you very much for listening, and see you this time, same time next week, when we'll continue with our revision. And remember that the revision videos are, there's a folder set aside. There's a folder set aside, and in there are the links, or they're the revision videos. I don't think these are on YouTube. They probably are on YouTube, but they're in Blackboard as well. And there's just these little videos. Watch those, watch these, and get 50% in the exam, because that's the maximum you can get from me. So that's it. Thank you very much, and I shall see you next week. Okay, so I'll stop recording now.